Hi guys, today we are going to report about propositional satisfiability. So let's begin. What is propositional satisfiability? Propositional satisfiability is a decision problem in logic, pivotal in computer science and artificial intelligence. If the variables that make up a compound proposition have truth values assigned to them, then the proposition can be satisfied. If there isn't a suitable assignment, the compound proposition can't be satisfied. Propositional logic is a fundamental branch of logic dealing with proposition statements that can be either true or false. So it is also known as widely applied in computer science from the circuit design to AI, where complex problems can be reduced to SAT instances. In SAT, we work with variables P, Q, R, and S, along with logical operators N and OR. For simplicity, we can represent the true as 1 and false as 0.
So continuing to the next slide, this is an example. So the value true corresponds to 1, while false signifies 0. The symbol that arrows goes up signifies and both numbers are 1 true. The ultimate result is true. The symbol in the arrow goes down represents OR. When one number is true and the other is false, the resultant value is true. Moreover, when both numbers are false, the conclusive result is false. So in the next page, we have this example. So just take a good glance of it. So let's find out whether the following compound proposition is satisfiable or not. First, we determine the satisfiability by reasoning about the truth values instead of using a truth table. We see that above propositions is true when P, Q, and R have the same truth value. Hence, it is satisfiable as we have found at least one satisfying assignment. The truth value table of the example above as it follows, which verifies the argument already presented. It is important to note that when the number of variables grows, the number of rows in the truth table grows exponentially. Since we have variables only has two possible values, that is true or false, a truth table will have two rows where n is the number of variables. In this example above, we have 3 variables, so we have 8 rows. Similarly, if we have 1,000 variables, the number of rows of the truth table will amount to 2 over the power of 1,000. It doesn't practically seem possible to generate such a large truth tables to prove the satisfiability of a given compound proposition. Hence, the truth table are not often considered an efficient option.
So these are the applications and benefits of SAT. In terms of hardware and software verification, number 1 is SAT plays a crucial role in formal verification, a process used to ensure that hardware or software systems meet specified requirements. Number 2 is by representing system specifications and properties as logical formulas. SAT solvers can determine the correctness of designs through exhaustive search. Number 3 is bug detection and error correction. SAT-based formal verification can help in bug detection by exhaustively searching for logical inconsistencies or violations of specified properties. Once bugs are detected, the correction process involves modifying the design or code to eliminate these issues. Number 4 is complex system validation. It encompasses the entire process of confirming that a complex system, which may involve both hardware and software components, meets its requirements and functions correctly. And then number 5 is its industry-wide application. Its applications on different industries such as in the aerospace industry, it is crucial for validating avionics systems. In the healthcare industry, it ensures the reliability of medical devices. And in the manufacturing industry, it is vital for ensuring the proper functioning of automation and control systems. Next up are the benefits of SAT in terms of automated planning. Number 1. SAT is utilized in automated planning to optimize scheduling processes in various domains. Whether in manufacturing, transportation, or project management, SAT solvers help find efficient schedules that satisfy given constraints. Number 2 is resource allocation. SAT solvers contribute to optimizing resource allocation by efficiently assigning resources such as manpower, machinery, or time to task. This is crucial in industries like manufacturing, where efficient resource utilization directly impacts productivity. Number 3 is decision support systems. SAT solvers are used in decision support systems to conduct scenario analysis. They help decision makers explore different scenarios and make informed choices based on the optimization of resources, costs, and other relevant factors. Number 4 is real-time systems. In real-time systems, SAT solvers can assist in dynamic scheduling, where schedules are continuously adapted in response to changing conditions. This is critical in domains like transportation and manufacturing, where real-time adjustments are necessary. And then number 5 is logistics and operations. SAT solvers contribute to optimizing routes and logistics, minimizing transportation costs, and improving delivery efficiency. This is applicable in supply chain management, courier services, and other logistic-intensive industries. Next up are the SAT algorithms. First up is the DPLL algorithm. The DPLL algorithm is a cornerstone in the field of propositional satisfiability solving. Named after its inventors, this backtracking algorithm is designed to efficiently determine the satisfiability of propositional logic formulas. Next up is the CDCL algorithm. The CDCL algorithm represents a significant advancement over the DPLL algorithm. Incorporating conflict-driven techniques to enhance efficiency, CDCL stands for conflict-driven clause learning, and it has become a standard approach in modern SAT solvers.
The presented text introduces the backtracking algorithm as a versatile strategy applicable to combinatorial, optimization, and constraint satisfaction problems. Backtracking involves incrementally building a solution candidate, and crucially, if at any point the algorithm determines that the current candidate cannot lead to a viable solution, it backtracks to the previous decision point to explore alternative options. This iterative approach is fundamental to the algorithm's working mechanism, emphasizing the exploration of different paths within the problem search space. The algorithm effectively handles failures by recognizing the inability to complete a candidate and utilizes backtracking to reconsider prior decisions, allowing for the exploration of alternative paths to reach a solution. The provided text sheds light on the formidable challenges associated with solving SAT or Boolean satisfiability problems, particularly as the computational complexity tends to exhibit exponential growth with an increase in the number of variables or clauses. It emphasizes intriguing phenomenon of phase transition in SAT problems where the difficulty of solving them experiences abrupt increases, rendering it challenging to predict the required computational effort for specific stances. This lays the groundwork for understanding the inherent complexities in SAT problem solving. In conclusion, it encapsulates the paramount importance of addressing the intrinsic complexity of SAT problems and advancing algorithmic efficiency. It outlines ongoing efforts focused on developing strategies to overcome the challenges posed by diverse instances, ultimately seeking to enhance the scalability and effectiveness of SAT solvers. The narrative paints a dynamic picture of the evolving landscape of research in this critical domain, showcasing the persistence and adaptability required to tackle the multi-phase issues associated with SAT problem solving.
Propositional satisfiability is essential for understanding this fundamental concept in logic and computer science. It highlights practical applications in hardware and software verification, automated planning, and emphasizes the significance of SAT in artificial intelligence. Imagine you're trapped in a mysterious room with 3 doors: gold, silver, and bronze. Each door is locked, and the only way out is to choose the correct one. Above each door hangs a cryptic clue. Gold means it is true only if the silver door is false. Silver means it's true only if at least one other door is true. And bronze means it is true if and only if exactly one other door is true.
Knowing that one of these statements must be true and the others is false, can you determine which door leads to freedom? This seemingly simple riddle translates to a complex propositional satisfiability problem. Let's represent the statements as variables, such as G, B, and S. G for the gold door is true, S is the silver door is true, and B, the gold bronze door is true. Now we can rewrite the clues as Boolean formulas. Such is the first number is that G is true if and only if S is false. And or you could say that S is false if and only if G is true. The next example is a disjunction between the three variables, and it means S or G or B is true, and it translates to at least one door is true. And for the last example, there is an exclusion rule, and it says there exactly one off. Now let's just say B if and only if what's this called G or S or B is true, meaning the other two must be false. Finding a satisfying assignment for these formulas, meaning assigning true or false values to each variable that makes all formulas true, is the crux of the SAT problem. In this case, the solution is G is true, the gold door is true, S false, the silver door is false, and B false, the bronze door is false.